Hi guys, today we are starting into a new topic. We are going to be examining what we call parent functions. So what is a parent function? The parent function is the simplest function with the defining characteristics of the family. Functions in the same family are transformations of their parent function. Okay, here's our first one, the constant function. And this is a little hard to see, but it's really just this flat line right here, right? A constant function is just a flat line, right? Here we can see it's this line probably looks maybe like x equals 1, or excuse me, y equals 1. And it is always f of x equals c, some numeric value. Its domain is all of the real numbers, right? So negative infinity to positive infinity. Its range, it only has one possible y value, so its range will just be this value c. It has no zeros. It never crosses the x-axis. And it's what we call symmetrical to the y-axis, meaning that if I were to, cover this, I could, hold up a mirror and it would be identical on this side, right? I could reflect this half onto this, and they would be the same line. The second parent function we're going to look at is what we call a linear function, right? We've seen these before. This is a line. The simple parent function of all linear functions is f of x equals x. All real numbers are its domain. It has the range of all real numbers. It does have a 0. It goes through the point 0, 0. That's where it crosses the x-axis. And we say in this case it's symmetric to the origin, meaning that the origin is this value 0, 0, and it has a symmetry that's defined on both sides of this. And we'll see other functions that are symmetric to the origin. So a constant and linear, that's our first two parent functions. Next is our quadratic function. We looked at these a lot last year, right? This is my parabola. Its domain again is all real numbers. The parent function's range value is y is greater than or equal to 0, including 0, right? It does go through the point 0, 0. That's its, ironically, that's its 0, right, is the origin. And it is symmetric this time to the y-axis, right? So we have this piece here that's a mirror reflection across the y-axis of the piece on the other side. If you notice, these functions are just ascending in powers, right? This would be, it has a component, an exponent of 0, right? We could think of this as having like x to the 0. This would be x to the first, x squared, and now x cubed. The domain of x cubed is all real numbers. The range is also all real numbers. It does have a 0 at 0, 0. And its symmetry is to the origin. So again, to this point right in the center is where it's symmetric. And if we notice, we can see this symmetry, right? That as it comes off, it spirals out in this symmetric way to this point 0, 0, rather than being symmetric to this axis. Next, we've got the square root function. Recall that is only defined for the first quadrant, right? So our graph is just this line here. Its domain is that x is greater than or equal to 0. Recall you can't put anything there. The square root of 0 is defined to equal 0, but we can't put a negative value in there. Otherwise, we end up getting into imaginary numbers, which we will look at later into a lot of detail. Here's the interval notation for that domain. The range here is also that y is greater than 0, because this will infinitely rise as we go out this side. Its 0 is at 0, 0, But it has no symmetry because this is only defined in one quadrant. We do not have a piece here. And it's fascinating because we'll see that here with the cube root function that we actually end up having a symmetry that we don't have because if you recall, we can have negatives underneath the cube root, but we cannot have a negative x value underneath a square root. Otherwise, this becomes an imaginary number. The domain of a cube root function is all real numbers. The range is all real numbers. It's got a 0 where it crosses through at 0, 0. And it is symmetric to the origin, right? We see this symmetry coming out, that these lines trace out symmetric to this center point. The absolute value function, f of x equals the absolute value of x. We get this kind of triangular shape. The domain of this is all real numbers, right? You can plug any value into the absolute value function. The range is always y is greater than or equal to 0, right? We include that point 0. The absolute value of 0 is just 0. Recall absolute value is that distance from 0 on a number line. Here's our interval notation. It does cross through this point 0, 0, so that is my 0 on the for this function, right, where it crosses the x-axis. And it's symmetric to that y-axis, right? We can kind of see that this is a reflection of this. Next, we've got rational functions. And I'm going to outline this because it's hard to see, but we've got this. It's a function that has kind of two pieces. And here at this, where x equals 0 on the y-axis, we've got this point where it's this function is undefined. If you recall, we cannot put 0 on the bottom of this fraction. That's why this graph never crosses this value. So if you notice, when we're coming in this way, it actually, as we put larger and larger, very tiny negative fractions in this goes down towards negative infinity. And as we approach 0 and put smaller and smaller numbers in here, we actually get something that approaches positive infinity. And there's a special line that crosses here that we call an asymptote. And we are going to be looking at asymptotes also in great detail. The domain of the rational function is all real numbers except 0. So we've got this two sets here, right? Negative infinity to 0, 0 not included, right? Because this function is never defined at 0 for x. And then from 0 to positive infinity. We also get that same value for the range because there is another asymptotic value that runs this way that we cannot cross this x-axis. This function never crosses the axes unless it's been shifted away from this parent function. It has no 0, but it is symmetric to the origin. These are two functions we did not get a chance to really look at in the spring, but we'll look at them this year. We would just only briefly look at them in the spring in Algebra 2. This function is what we call, it starts here. It's our exponential function, meaning this is what models the growth of life, right? If you have two things and they keep multiplying by themselves by 2, right? Multiplying 2 times 2 times 2 any number of times. This is a function that models life. Its domain is all real numbers, right? So it comes out here and it may get infinitely close to 0, but it always can take on another x value going out this way and going this way. Its range, though, is always greater than or equal to 0, right? So it can come here and kind of touch 0, but it's not going to go below that, right? Because 2 to the 0 would be 1, right? And then as we put in smaller and smaller values, we'll get down to 0, but we'll never go below that. It has no zeros, right? It gets close to this 0, that's why we include it, but it really actually doesn't cross that axis, and it has no symmetry. Here, if we notice, it does not curl off in the same way from here or mirror itself here. It's this non-symmetric function. Our last one here is the logarithmic function. Its domain is that, and we will also look at these, we would say this is f of x equals log of x. Here the domain is x is greater than or equal to 0. Right, we can only be on this side of the axis. The range, though, is all real numbers. This can actually grow very large. It has no zeros, and it is not symmetric, right? Again, it's like this function where we don't see any symmetry. And these two functions we'll look at in depth in two different units. Okay, we're not going to get into translations today, so I'm going to stop my video and we'll do some examples.